Okay, so our lesson today deals with what we call a U-substitution. And in particular, we're going to deal with the U-substitution for the power rule. But in order to explain where this comes from, let me go back and look at chain rule, because U-substitution is kind of the integral form of the chain rule. But let's look at the chain rule. In the chain rule, if we took the derivative with respect to x of, say, I don't know, x to the fifth, of course that was equal to 5x to the fourth. That's very straightforward. An example of the chain rule might be something like, I don't know, instead of x to the fifth, maybe 2x plus 1 to the fifth. And when we took the derivative of that, the 5 came down in front. We took that 2x plus 1, and brought it to the 5 minus 1, or fourth power, times the derivative of what's inside. So basically, what we're doing is we're going to take the derivative with respect to x of some u raised to a power of n, where u is just some function of x. In our example here, it was 2x plus 1. And so when we took the derivative of that, the n came down in front. We then took the u and raised it to the n minus 1 power times the derivative of what's inside, which I'll go ahead and call u prime. So this is what a general kind of rule would look like for the chain rule. Sorry, I left my prime out there. So let me take that same rule and let's go ahead and do this, now that we have a little understanding of it, for the function u raised to the n plus 1 power. So if I do that, what I'm going to get then is n plus 1 times u raised to the n plus 1 minus 1, which would be u to the n, times u prime. So basically, I just replace the n with an n plus 1 in this equation. Now, since it is an equation, I will be allowed to do anything I want to one side as long as I do the same thing to the other side, and that includes integrating both sides. So if I come in here and I decide I want to integrate, for example, the left-hand side of this equation, that's perfectly fine as long as I do the same thing to the right. So I'll go ahead and integrate the n plus 1 times the u to the n times u prime with respect to x. And let's see what this gives us. Starting over here on the left, I know that integration, and that's the integration part, and differentiation are opposite processes. So on this side, I'm going to be left with just a u raised to the n plus 1. On the other side, notice that we are integrating with respect to x, and the only pieces of this that would have an x in it would be these pieces. This n plus 1 is a constant, and we're allowed to bring those constants in front. So this looks like n plus 1 times the integral of u to the n times u prime dx. And then if I divide both sides by n plus 1, I get the form that we're going to look at today for our u substitution, and it is that the integral of u to the n, just kind of switching sides here, times u prime dx will be equal to u to the n plus 1 over n plus 1 plus c. Now, we're going to go ahead and look at this, and this is the form we're going to use, but let me look at it compared to a basic rule so that you can see how these two play out. And then I'll tell you a little bit about the notation that I'm using here, because I tend to do it a little bit different than some people do. When we go through this next section, we're going to be looking at U-substitution rules, and pretty much for every basic rule that we see, we will have a corresponding U-substitution rule, and they'll look similar. In other words, we had a basic rule for x raised to a power. The integral of x raised to the n power with respect to x will be equal to x to the n plus 1 over n plus 1 plus c. And the corresponding u substitution rule means if we're integrating something other than an x raised to the n power, then what we need is a u prime with respect to x, and when we have that, we're going to get u to the n plus 1 over n plus 1 plus c. The main difference here in the two is that the u substitution form adds this u prime thing, and you can kind of think about it this way. When we differentiate we add a u prime. When we integrate, we need a u prime. So this is the form that we're going to spend the rest of the time today going over. Now, before I go on and do some examples here, I want to say one more thing about this, and that is that this is probably not the form that you're going to see in most of the books you pick up. The form you're going to see in most of the big books you pick up is that u to the n times du will be equal to u to the n plus 1 over n plus 1 plus c. What I'm saying here is that du is actually the same thing as u prime dx. Let me show you what I mean. If u is a function of x, then u prime dx is nothing more than the derivative of u with respect to x times dx. And of course the dx's cancel out and you get du. So these two statements that I'm showing here are actually the same, they just look different. And I kind of prefer the one that I wrote just simply because it makes it clear what it is we need. All right, so in the next video, we're going to look at some examples here of how it is we can calculate integrals using U-substitution.